Can anybody hear me? Can you please let me know if you can hear me? This is Mike Smid. I'll be speaking today. I just want to clarify that you can hear me properly. Thank you. Okay, I'm going to be starting shortly here. I'm going to wait a couple more seconds. What I'm going to do is actually I'm going to kick it off by first showing everybody a brief video. And when I do the video, I just want to confirm actually that everybody can properly hear the audio when it's playing also. So if you do not hear the audio when the video is playing, just please let me know, and I'll figure out a different path. We'll just start the presentation, okay? But this is a pretty interesting and compelling video to start off with. So I'd like to just start with this, and then we'll go from there.
The experts at Carrier have done it again with a surge-free chiller so tough.
You may just forget how efficient it is. The Carrier 23 XRV, the lifecycle chiller. The robust, dependable performance of 23 XRV chillers stems from Carrier's advanced Foxfire compression technology. Brilliant in its simplicity, the only moving parts are the 3 screw rotors and variable speed electric motor. Capacity is controlled by simply regulating motor speed, completely eliminating the need for guide vanes or slide valves, while the Semi-Hermetic R134A design eliminates the potential refrigerant leaks and maintenance associated with shaft seals and purge units. Long bearing life is assured by working with the laws of physics instead of against them. Conventional twin-screw compressors experience unbalanced load forces, but the innovative tri-rotor design ensures cancellation of axial and radial loads so effectively that at ASHRAE conditions, the lowest bearing life in the compressor is over 50 years. The simple and direct design, low component count, and long bearing life mean there is no scheduled compressor teardown or inspection required. But it's the fundamental difference in the 23XRV's compression process that delivers a crucial advantage over centrifugal technology. Centrifugal compressors rely on tangential velocity to move refrigerant gas through an open path between the evaporator and condenser. If the compressor cannot generate enough force, the gas will flow in reverse, a phenomenon known as surge, and the chiller may shut down. Unlike centrifugal compressors, 23XRV compressors have no open path and no potential for surge. As the rotors spin, refrigerant gas is drawn into a confined volume, compressed, and then discharged. This positive displacement compression process provides more robust and flexible operation. In 2005, field data recorders in Arkansas documented 23XRV operation without any operable cooling tower fans. The chiller endured entering condenser water temperatures of over 105 degrees during the 12 hours it took to repair the tower fan. The 23XRV chiller operates through conditions where other chillers would simply shut down. The machine is running without issue. It has 107 degree entering condenser water temperature to the chiller itself. Basically what they find out is that it's running about 75% full, and there's also some other issues with the tower itself. We operated with over 90 degrees condenser water for days at a time. The tropical storm filled my tower with debris. The bypass valve was stuck at 80% bypass. The condenser pumps were undersized. Our old chillers couldn't do that.
I was really surprised the chiller was still running.
It was operating just fine. This inherent advantage in compression technology provides confidence in an imperfect world and delivers another striking advantage over other technologies: more speed reduction. And as we all know, more speed reduction means more energy savings. The 23XRV can achieve 75% speed reduction versus just 35% for centrifugal compressors. In addition, centrifugal speed is a function of load and weather. Warm weather can limit centrifugal speed reduction and energy savings potential. In contrast, 23XRV speed precisely tracks capacity, so load reductions are matched by energy-saving speed reduction in any climate.
The Carrier 23XRV chiller is used due to its efficiency. It was in line with our direction for Green Mark Platinum Award. The initial target was to achieve 40% electrical savings on the chiller plant system. Currently, we are already close to hitting the target.
Because of its simple, speed-optimizing operation, 23XRV chillers deliver balanced efficiency across a wide range of conditions, which can help earn lead credits in the energy and atmosphere category. When performing whole building energy simulations, factors like local weather, building load profiles, and the number of chillers employed are taken into account. Studies have shown that the 75% load bin often accounts for 60 to 75% of the ton hours. In contrast, the 50% and 25% load bins typically account for less than 20% of the ton hours. 23XRV efficiency at 75% load is up to 17% more efficient than other variable speed chillers. The industry has taken notice, previously awarding the 23XRV the AHR Expo Innovation Award in the Green Building category. Reliable, robust, dependable, efficient. A chiller so simple, so robust, you may just forget how efficient it is. The 23XRV is the life cycle chiller. Turn to the experts. Turn to Carrier.
Okay, there we go. All right, so I think we're going to start here, and I'm going to show you the 23XRV. I think everybody could probably hear me fine now, I believe. And if you can't, please let me know. Okay, so we're going to talk about the 23XRV. It is the most efficient chiller in the industry right now. In fact, a couple months ago, we basically have a part load optimized compressor, and it was the first chiller ever to break the 0.299 kW per ton IPLV barrier. So very impressive chiller, and we're going to go through that today here. I just want to make sure that we don't have anybody, just want to make sure the noise, let's see here, let's see. Okay, so I want to talk to you a little bit about how the Carrier product line has evolved. Okay, basically, short 7 years ago, we had this product line right here. We had the 30HX, which is our dual screw rotor screw chiller, dual circuit screw chiller from 80 to 265 tons. And above that, we basically had a 19XR without a VFD, and then we had a 19XRV with a VFD. So now, flash forward into today, the Carrier has really invested heavily in the market, in their air-cooled and their water-cooled chillers. And now we have the following scenario. We have the good lineup, which is our modular 30MP, which I'll kind of briefly discuss each one of these. And then we have a 30HX from 80 to 265, a 30XW from 150 to 400. We still have the 19XR XRV in our product line, and really what we're going to go over today is the 23XRV from 250 to 550 tons. The 30MP is a great little product that we basically Carrier launched a couple years ago, and it's a modular design from 15 to 45 tons, standard cooling operation, but it can operate and produce heat up to 140 degrees standard without any issues at all. You can do full condensing water cooled, or you could team it up and put some remote condensers on a roof also. The heat reclaim, you can use it for potable water, or you can use it for reheat. But really, the most important thing I think is that we often compete with that multi-stack product in the modular chiller business, and now we have a modular piping package that goes along with this machine, which you can see on the next slide. So we come with this Victolic piping connection kit, and we could pipe up to 8 of these machines in parallel to operate the chiller plant. So now I have 8 of these machines that I could modularly put in. They all fit in an elevator for replacement applications. You can use some of them for heat reclaim, which is a presentation I'll be going over shortly in the following month. The workhorse really of our industry, which you showed, the old part of the old product line, which is our 30HXC dual circuit, fits through a door, absolute robust chiller. It's been out there for a long time, the first chiller ever designed with screw compressors in 134A. Then we have one of our new machines which we have in our lineup, which is called a 30XW, which is our heat reclaim chiller and our standard chiller. It'll be single circuit or has dual circuits, 300 to 400 tons. It will fit. It'll be about 48 inches wide. It can produce up to 140 degree heat, and it's got very good part load values. And then we also have our centrifugal, which is our 19XR XRV. Very good low install cost, very good efficiencies, proven, have a ton of them in the marketplace, has a great track record, and we use that. But really the main focus today is going to go over the 23XRV. And the 23XRV has just been an absolute great machine that we have had in this marketplace. And right now we have a great deal of these machines up and running. And if after this presentation, if anybody actually wants to go see one running, hear one running, talk to end users, you just need to send me an email and talk to me, and we'll set that up, because our best salesperson is actually the end user, because these machines are absolutely robust and they run fantastic. So we're going to go through the introduction, the program history, the compression, which is the most important part, industrial design, and then I'll start talking about performance a little bit. In the brief video, we mentioned that this was the 2008 ASHRAE Product of the Year, Green Building Product of the Year. This competed against every type of product that's in this business. So when we talk about green product, this is going against green roofs and going water, just everything that you put in a building. This is the Green Product of the Year. So it's a pretty fantastic accomplishment from Carrier to be the AHR Expo Innovation Award Green Product of the Year in 2008. It's a fantastic machine. So the reason why we did this today, we've done this presentation a couple times. Mainly, Carrier has now introduced what we call the Q compressor. Okay, and what the Q compressor is we basically have it starts from 250 to 400 tons, and then 400 tons to 550. Previously, we had one compressor that handled from 275 to 550, where 400 to 550 was a sweet spot. Below that was still very good efficiencies, but it could get better, and that's why we introduced the second compressor in this machine. Oops, hold on. Okay, so when they introduced the 23XRV, so what we do is we have a standard VFD, standard on the machine. We optimized around 134A. We're using the same ASME pressure vessels that we have for the 19XR and XRV. And now we have the next generation screw compressor, and also the two sizes, so it completely fills the lineup from 250 to 550 tons with industry-leading part load efficiency. I mentioned before that we basically broke the 0.299 kW part load value with our new part load optimized compressor, and we'll go through that in a bit. I mentioned before, this is something that we feel, obviously the majority of every manufacturer uses 134A refrigerant. There's one manufacturer that are still sticking to their guns with 123, and that refrigerant, they can no longer sell chillers in this U.S. market after 2020. So that's less than 7 years away. We are talking about operating life before that chiller plant has a refrigerant that is basically extinct, in that there'll still be refrigerant out there, but the only place that it's allowed, 123 is produced, is for centrifugals for that manufacturer. So we feel with no phase-out date with 134A, 134A was obviously the right choice for refrigerant. We're going to briefly talk about program history. Again, what we did is we looked at designing around 134A. We have the tri-rotor screw compressor, which I'll go in depth with, and then we have a variable speed drive. We don't produce this chiller any other way. We don't put a Y delta starter. We don't put a solid state starter. We only produce it with a VFD. The machine's inception was basically in the late 1990s, early 2000s, when it was the technology was developed in the United Technologies Research Center, which is one of the largest privately funded R&D facilities in the U.S., and that's where the 23XRV had its birthplace. So after it was proven at the United Technologies Research Facility, it then went and was implemented by Carrier for one goal and one goal only, and that was to become the world's most efficient and most reliable compressor in the marketplace. And we did that, and they hit it out of the ballpark with it, and we'll briefly discuss that later on here. So what they did is it went through the most extensive field trial program they've ever had. So they have thousands of hours of operating in factories, hospitals, office buildings, temporary cooling, hot, cold climates. Everything you could think of, they tested in these conditions. So this is where this machine starts getting interesting, which is basically the compression part of it. The machine, again, it's Carrier makes the compressor in Charlotte, North Carolina. It's made from they have two sizes, 250 to 400 and then 400 to 550, specifically designed around 134A, a tri-rotor design. And one of the things that's most important, because people think of screw compressors, and they think of two things when they think of screw compressors. They think, first of all, that it's going to be loud, and it's going to be a maintenance nightmare because of the past issues with screw compressors and slide valves. Well, we eliminated the slide valve, and I'll show you in a video in a bit that this is actually quieter than a centrifugal. Okay, so we'll go through that in a bit. If you look at the way a traditional twin screw compressor works, as I have refrigerant that's basically passing through this twin rotor, it is actually forcing that rotor apart. And the typical twin screw is actually longer, so there's a little more slop in it, and as you have slop, you get inefficiencies, and because of those forces that are basically forcing that rotors out, we have huge bearing loads, and when we have huge bearing loads, we have a lot of oil that we have to lubricate, and as we have more oil to lubricate, we lose efficiency in the machine itself. So what Carrier did is we basically have what we call the tri-rotor screw compressor, and with the tri-rotor screw, we basically have forces that cancel both axially and radially. Okay, and that is shown better in this picture here, where you can show the compressor here, where their forces are canceled axially and radially, and basically, so the axial and radial forces are canceled. With that, we have the lowest bearing life on this machine is 500,000 hours. Okay. With that, you basically do the math, 365, 24/7, it equals to 57 years. It never has a stop major in its life. Okay, so it doesn't have a 10-year overhaul, doesn't have a 20-year overhaul. Now, because of that, the end user does not have to invest in that 10-year or 20-year overhaul, which could cost as much as $40,000 to $50,000, and I've even heard higher in some cases. Hold on a second. There we go. So goal was to maximize the efficiency and the reliability. So again, we have a tri-rotor. Because the forces cancel, we operate with as much oil that can fit in the palm of my hand. So less oil makes more efficient. Now I have larger surface area and discharge area on the screw. Larger discharge area in the screw means I can get more efficiency out of it. So it's higher efficiency, very little moving parts, so it's got high reliability. I eliminated the slide valve, and it operates with a VFD standard. Okay, look at the, again, motor dilemmas, motor designer's dilemma. I have a design for efficiency or low inrush and power factor. How do we handle that? We use a VFD, and it's got a 0.99 power factor across all loads. Okay, here's the cutaway of the machine itself, and if you actually have a chance to look at this machine operating, You have, I mean, look at the compressor in the cutaway. It is an absolute tank of a compressor. Okay, so we have 3 moving parts, the 3 rotors. The good thing about the screw, most screws can only operate down to 70-degree entering condenser water, and that's because of the oil lubrication system. This has its own independent oil lubrication system, and we're able to operate with condenser water temperatures down to 55 degrees. So that is really, really important. Again, industrial design. Positive displacement, so the machine cannot surge, quickly adapts to system change. We'll show you that in a bit. 134A, no purge. Semi-Hermetic motor. It's not an open drive motor like an open drive centrifugal manufacturer produces, so I have no shaft seal or shaft seal alignment issues. And the cooler and condensers are ASME pressure vessels. Again, positive displacement, can't surge, 3 moving parts, very fast response. So we look at this design here and say, I don't have, I have very little, I have no redundancy built into this. So I have a cooling tower, a condenser pump, the 23 XRV, a chill water pump, and an air handler. What happens if something happened to one of those components? So as you saw in the video, we have a snapshot, and what happened is this was one of the first beta sites that Carrier had. And with this, they basically had a machine running with 300-degree tower in blue. So you can see here the blue is 300 tons. And we are running with around 72-degree entering condenser water. And then what happened was a condenser water tower fan failed, and my condenser water temperature shot up to 105 degrees. Okay, when that did that, the chiller reacted, settled down, and operated at around 150 tons. It wasn't operating at 300 tons because now my tower water is hot, but it was operating at 300 tons. Okay, I mean at 150 tons, providing some cooling for the facility. And after 12 hours after it was repaired, you could see the tons shot up, and then it went back to operating at steady state 300 tons. There's not a machine in the marketplace that would do this. A centrifugal couldn't because it would surge. The screw compressor could because it will not surge. The refrigerant cannot flow backwards. The other thing I forgot to mention here when we talk about compressor reliability, and we talk about great designs and how robust this machine is. This machine, we have a compressor that is sitting on the floor waiting for the first compressor failure. And we have produced this machine many, many, many times over, thousands of installations across the U.S., all over the world, in all different climates and conditions, and we have never had a compressor failure on the 23 XRV. So very, very good track record. Hold on a second. Okay, so the reason why it can react so fast is because basically we have sensors. It goes to our control panel, which then adjusts the VFD. I have no actuators, solenoid valves, or slide valves. The machine can also handle 80% rate of change in flow, which is really important. So variable primary flows, variable primary flow with this chiller is absolutely fantastic. Again, 3 moving parts, 57-year individual lowest bearing life, no stop major compressor overhauls, no purge, no shaft seal, no slide valves. The end user is, it's a fantastic machine for an end user who's going to look at the overall life cycle of a chiller. We discussed earlier here, and I'm going to show you here again the slide where we basically said that the 23 XRV can achieve 75% speed reduction. The ideal fan laws of a centrifugal limit it to only 35% speed reduction. Now, what a VFD does on a centrifugal is it is a lift reducing device. So it's not a part load device, it's a lift reducing device. So we could be operating here at 65% speed, at 35% speed reduction. And let's say the cloud is hanging over the sun, and then the sun goes up, the tower water temperature goes up, and therefore now my speed of my centrifugal, because the wet bulb temperature in the tower has gone up, the speed of the centrifugal will have to increase. Because on a centrifugal, the VFD tracks the wet bulb temperature outside. Okay? Whereas on the 23 XRV, speed equals load. It is the only part load, part lift chiller in the marketplace. Fantastic for efficiencies in true part load operation. Show here basically how it can respond. Again, here we cut the flow in half in less than a minute, and the machine quickly stabilizes and operates. Look at operating with 25% load with extremely high condenser water temperature. So I got 25% load, 98-degree entering condenser water. Try that with a centrifugal. It will not operate very well. It will, most cases, it will probably surge. Reduce the flow 50% in 35 seconds. Again, we mentioned we can operate with 80% rate of change in flow. Positive pressure. It doesn't have any purge. It doesn't have any associated leaks or maintenance associated with the purge. Semi-Hermetic motor. The motor is refrigerant cooled. Okay, so it's going to operate in the ambient temperature of a refrigerant, about 85 degrees, whereas an open drive machine can operate in higher ambient temperatures. It doesn't have a shaft seal, which associated leaks, and then changing of the shaft seal later on in its life. Again, it's an overall life cycle chiller. Heavy ASME duty pressure vessels. Like most people who make 134A designs, it's an ASME pressure vessel. These are what I call the little things, okay? You could see here on the top we have our evaporative tubes and we have our condenser tubes. But if you look at the bottom picture, it's a dual grooved tube sheet, okay? There's manufacturers that produce their tube sheet where they only provide a single groove. There's some that just provide epoxy coating to basically properly put the tubes in the tube sheet. We use a double grooved tube sheet to provide a superior fit to make sure that we have the refrigerant water side to ensure we have a very tight seal between the refrigerant and the water. Nozzle and head, marine water boxes are options you can get. Quick connect sensors, again, I said the little things. If you change out a sensor, I don't have to remove the complete charge of refrigerant out of the machine to do it. We can just change this simple with the thermal wells and the Schrader fittings. We could change the sensor out. Very nice situation. Again, it's become so reliable and it can operate in so many different conditions that the carrier rental fleet has standardized on the 23XRV for the rental fleet because it's got a small footprint and it can operate in any conditions. It can operate in Chicago, it can operate in Miami, and you cannot say that about centrifugals. Bolt together design, positive displacement, in-charge refrigerant storage, factory-mounted VFDs, single-point electrical. The majority of everything we do today is a replacement market. So most of the cases we have our machines are being disassembled and reassembled. We do this very easily. The machine is completely bolted together, okay, and it's bolted together and you could take off the compressor, VFD, cooler, condenser and get it in the building, and we can have carrier, our servicing arm, do all that work if you wanted to, or so if that was the desire. Again, 134A showing the phase-out dates. I'm not going to go in depth in this, but basically that's why we feel that there's no phase-out date, so that's the right refrigerant. From a safety standpoint, 134 is low toxicity with no flame propagation, whereas the 123 is higher toxicity with no flame propagation. In chiller storage, we ship every one of our chillers. It has an isolation valve package on it, so you can store either the refrigerant in the cooler or condenser to do service work. Saves time, reduces service expense. Unit-mounted VFD. This is one of the things I'm going to go to briefly here. Standard is a 65K interrupt. Optional is 100K is optional. The one thing is we can get the VFD with an IEEE 519 filter, or we can use a standard VFD on it. Either way, but one of the most important things is that the drive is going to be refrigerant cooled. It's not water cooled, it's refrigerant cooled. Okay, that's the factory mounted drive on what we have. I've seen jobs where basically they have a water cooled drive, and they have the strainer that gets clogged, and when the strainer gets clogged, that means we have alarms that our drive is overheating, and that requires a service call to go out there and fix the strainer, and it's a nuisance for both the end user and the servicing technician that has to go out and fix it. So those are all, you know, from a refrigerant standpoint, all our losses are included in our selection. So we don't leave our losses external to someone else to handle. All our losses and what our true operating kW per ton is in our sheet, our selection that we send to the contractor or end user or engineer. Let's talk a little bit about chiller efficiencies and performance. Okay, so I mentioned before that we broke the 0.3 kW efficiency barrier with IPLV. Now I'm to kind of, we have a snapshot of one machine that's operating in Charlotte that's operating with continuous operation with 55-degree entering condenser water with measured part load values with 50% load with 55-degree entering condenser water at 0.21 kW per ton. This is an actual installed kW per ton that we're looking at in an actual install in Charlotte, North Carolina. So let's talk about chiller efficiency, and we'll go into this whole IPLV and why it's in my opinion, it's a little bit of a, you know, even though we have the best IPLV in the marketplace, I feel it's a trap, and it's not the correct way to properly measure efficiency of a chiller. Okay, so the chiller efficiency, if you look at it, compressor input kW is equal to mass flow, refrigerant flow times lift, divided by the cycle efficiency. So really what we look at is kW equals tons times lift. So when we look at the chiller operating, okay, from the condenser side of it, so for the refrigerant so basically our approach on the condenser water side, we have 95-degree leaving water plus a 2-degree approach on the refrigerant side equals 97 degrees saturated condensing temperature. To boil refrigerant, the refrigerant must be colder for the leaving chilled water. So therefore, if we have 44-degree leaving chilled water, we have a 2-degree approach. So therefore, we have 42-degree saturated suction temperature. The lift of a chiller is leaving to leaving. Okay, so it's my leaving chilled water, condensed saturated suction temperature minus the saturated condensing temperature. That's what lift is. Someone may say we can operate with cold water, and the answer to the next question you should say is, what is your leaving chilled water, what is your leaving condenser water temperature you need to operate with that machine? Because it's leaving water temperature, not entering water temperature. So when we look at this in compressor map on a pressure enthalpy chart, design day conditions, we're operating at A1, and basically what we have is our lift is 97 minus 42. That's our lift on that machine. When I can operate with colder condenser water, what we do is we reduce lift on a chiller. So let's say I have 70-degree entering water, 80-degree leaving, 2-degree approach. I have 82-degree saturated condensing temperature. If I'm able to operate with colder condenser waters, I'm colder condenser water, I'm reducing lift, and I'm reducing kW on the machine itself. Lower lift, lower work equals lower kW. And this is going to be a theme we'll talk about, and we're not going to talk about a phenomenon which we have called series counterflow. That's going to be one of the next webinars I'm going to do in January, which is going to be a webinar basically designed about chilled water plant optimization, and we'll discuss that later on. So when we look at chiller efficiency, and we say, okay, if you look here in red is a constant speed centrifugal. In blue is a variable speed centrifugal or screw, you could say. So on the bottom, we have percent building load, or ARI turn down. And on the left-hand side, we have kW per ton. Okay, so at the full load point, and full load happens very little, right? So full load is when I have my machine running at 100%, I'm at design conditions, and my building is at design conditions. That means it's fully occupied and loaded, and my machine is running at design 100%, and it's operating at design wet bulb temperatures in the tower and everything like that. But at that point, we have very similar operating points at 100% load point between a machine that's constant speed and a variable speed machine. if we look at a 2-chiller plant, let's say I have a minimum tower water of 55 here, and I have a design day of 85 degree entering condenser water here, and this is percent load of chiller. So I'm going to load up the chiller plant. So I'm going to start up, and I'm going to load up my one machine up to 100% load, and then I'm going to basically turn on the second machine at 50% load and ramp up those 2 machines to handle the remainder load of the building. So the interesting part here is at the design condition, 2 chillers, the 100% operating point is the same. Okay. However, if you look at that 50% point, both the constant speed and the variable speed machine are both operating at the 100% load point. The reason why the kW per ton in blue is less than red is because that blue machine, in blue, has a variable speed drive on it. As you hear me talking about variable speed drives on centrifugals, they track the weather. So therefore, as I'm at 50% building load, my condenser water temperature is reduced, so I'm able to reduce the speed on the centrifugal or screw, and therefore I'm able to run at lower kW per ton versus a constant speed machine. That's why VFDs make a ton of sense and in this marketplace, because we can operate with cold condenser water temperatures a lot of the hours. So let's look at the IPLV matrix. Okay, so I have the IPLV matrix, and again, the full load has 2 components, 100% load and design conditions. Okay, IPLV is weighted in the following factor. So we have 100% load point, which they say happens 1% a year, and I have a condition that it's operating with 44 leaving with 85 entering condenser water. The 75% load point is weighted at 42%, and that has 44 degree water and 75 degree entering condenser water. The 50% load point has 45% of the hours weighted to it, 44 leaving, 65 entering, and again, 25% load point, 12% of the hours is weighted, 44 leaving, 65 entering. Okay, so IPLV is a way to rate a single chiller in a single plant, typically without an air side economizer. So the real way to measure chiller plant efficiency is what we call system part load value. Okay, so we look at the actual load, local weather, we look at the load profile, the operating hours, economizer, analyze the pump and the tower energy, and look at the chiller staging. Okay, again, the IPLV was derived from a representation of an average part load for a single chiller. Okay, we need to look at all those other options when we're analyzing a chiller plant and look at system part load value. As I mentioned before, we have a ton of hours that can operate lower than 70 degree entering condenser water. On a building that operates 24/7, 73.8% of the hours we can operate with less than 70 degree entering condenser water temperature. In a building that's operating 12/5, we have 73% of the hours that have less than 70% entering condenser water. When you enter into air side economizer, it's slightly less than that, but it's still a high percentage of building operating hours with cold condenser water. Let's look at a Chicago 3-chiller plant, and I want to this is my whole snapshot of why IPLV does not work in a multiple chiller plant. Okay, and that's basically most of the chillers in this marketplace operate have more than one chiller in it. So let's look at point 1. Point 1 is our 100% load point. 100% load, 100% design. So the building is fully occupied, the chillers are 100% loaded, and we're on design day. How often does that happen? My guess, probably never. Okay, so we have the 3 chillers that run down to point 2. At the 66% load point, we lose a machine, and then we go to point 3, and then we basically operate down to 2 machines, down to point 4, then we go to 5, and then we operate with 1 machine from 0 to point 5. Okay, so let's look at the bin data from an IPLV standpoint. So the 100% load point is from 100 to 87.5%. Okay, that means point 1, 3, and 5 would be in that 100% load point. And that shows a representation of the line shaded in red. Okay, that is what the 100% load point bin looks like. Let's look at the 75% load bin. That would be from 87.5 to 62.5. And there, this is the 75% load point, and that would be dictated by everything shaded in green. Now let's look at the 50% load point, and the 50% load point is everything shaded in blue. Okay, and then we have the 25% load point, and the 25% load point is shaded in gray. Okay, now we live in Chicago, and we know that the majority of the time we operate with air side economizer when we can. So with air side economizer, that would be the line in blue, everything shaded would be the minimum building load, okay, which basically eliminates altogether the 25% load point. Now, if you remember when we were looking at the 25% load point, IPLV had 12% weighting factor on the 25% load point. That only favors one chiller in the marketplace. One chiller that has very good efficiencies at 25% load point at cold condenser water temperatures, and that is the turbocore machines out there in the marketplace. Okay, whereas if you look at traditional office buildings with multiple chillers, that 25% load point almost never happens. Okay, so if we look at the net result, our system part load value, the 100% value happens, we're saying 30% of the time. But it doesn't happen at 85-degree entering condenser water temperature. It happens with an average condenser water temperature of 75.9. Okay? The 75% load point happens 63% of the time with an average entering condenser water temperature of 71.5. And the 50% load point happens only 7% of the time with an average condenser water temperature of 60.2. And the 25% load point never happens. So again, when we look at the performance metrics, it's basically 100% building load, design day, buildings fully leased, fully occupied, full solar load, full equipment and lighting load, and full ventilation rates. Happens less than 1% of the operating hours per year, if ever. And then, of course, all chillers are sized to meet the building load exactly, correct? No, and that's, we all know everyone puts a little bit of safety factor when analyzing the chillers. So when we look at the point 1, 3, and 5, those are the 100% load point. Oftentimes there's a manufacturer out there saying, we had 30% of the hours in the 100% load point, that's why VFDs don't make sense. Well, if you look at that, they do operate at that high, at 100% load point, but they operate with cold condenser water. Because they operate with cold condenser water, we have the ability with the VFD to reduce the lift in the machine, centrifugal or screw. So that's why VFDs make sense at 100% load point. You can see that in this following piece here where we have chiller full load efficiency, 0.1, 0.3, 0.5. 0.1, constant speed machine, it reduces as the water temperature drops, we basically get better in efficiency. Variable speed centrifugal is in blue, gets better. 23 XRV, the machine we just talked about, 1, 3, and 5, even better than a variable speed centrifugal. And then what we have here is our part load optimized 23 XRV, which is the absolute best at 0.3 and 0.5. Okay. So when we analyze and compare the IPLV versus the SPLV, again, the 100% load point, we said, happens 1% of the time with 85-degree tower, where it actually happens when you analyze the building 30% of the time with 75.9 degree entering condenser water temperature. Okay, the 75% load point in IPLV said 42 was 75. It's actually 63 with 71.5. And the 50% load point used to be 45, 65, and we're at 7%, 60.1, and the 25% load point never happens in our system part load analysis. And this is a typical Chicago office building. So what we did is when we came up with our machine in the 23XRV, we have our part load optimized 23XRV. What we did is we sacrificed full load efficiency to better part load. So we basically lost 8% efficiency at the full load point that never happens, and we gained it at point 1 and 3. We're gained 5% and 8% at point 3 and 5. At the other points, we gained 2%, 7%, and 12%. And at the very low points, we picked up 13 and 16% with our part load optimized machine. And we gained 17% over here. Now, from a sound standpoint, our chiller, 85 dB standard, as we drop condenser water temperature, we lose 3 dBA, so it's 82 dBA. And then we have 78, 78 at the 75% load point, and we have 78, 78 at the other points also. Now, what I'd like to do here briefly is show you guys what we call our sound video.
Specifications is often no laughing matter. There are, of course, exceptions. In this episode, we encourage you to enjoy our volunteers' presentation of a topic that is, well, sure to get your ear. Listen closely and tell us what you hear.
Gentlemen, welcome. Would you like some sparkling clear water?
Yes, please.
Now this is very clear.
I wish everything were this clear.
I know what you mean. I was comparing the chiller submittals. One vendor was making a great deal of noise over sound.
I noticed they were talking about 75 dBA compressors.
Yeah, but that's 3 compressors. So if each is 75 dBA, what do you have with the overall product?
Well, I believe with sound in this decibel range, when you add 2 equal sources, then you add 3 dBAs, so that would be 78. Adding a third compressor, you must be close to 80.
Why don't they just tell us that? They're charging a great deal for this low sound.
Using a handheld sound meter, I measured the sound inside the mechanical plant and then again immediately outside the plant room door. There was a 14 dBA difference just by stepping outside the door.
So we're talking about the difference between 68 and 65 dBA outside the plant room door? Not dishwasher between 55 and 70 dBA.
Gentlemen, pardon me. I couldn't help overhearing you, but maybe I could be of some assistance. Take a look at this.
Get the whole story on sound. Carrier's award-winning 23XRV operates so quietly, you may just decide to talk about something else during dinner. Come hear the difference. Turn to the experts.
Okay, there we go. Sorry about that. So I wanted to make sure you guys understood. Let me just get back on track here. Okay, so I want to go on again and look at IPLV and compare another manufacturer who has very good IPLVs, but their IPLV ratings are better at the 50 and 25% load point, and that is typical. Chiller A is basically shows you a magnetic bearing type machine, and let's look at a multiple chiller plant. Chiller A is a magnetic bearing chiller. Chiller B is our 23XRV, our older compressor, and Chiller C is the 23XRV with a part load optimized compressor. You see at the full load, we look at the IPLV of 0.325 on the Chiller A. Our old Chiller B would be 337 part load, and I'm actually losing the, hold on a second. And then we have 0.314 part load optimized, comparing that one machine on Chiller C. When we look at the system part load value, we basically have 0.399 for Chiller A, 0.373 for Chiller B, and 0.362 kW per ton on Chiller C. So you have to analyze the chiller plant as a whole. The 25% load point almost never happens. The 50% load point has very few hours, and the overall life cycle cost winner will be the 75% load point in most multiple chiller plants. And we did a study. Carrier did a study across the world, and what they did is they basically analyzed a 2,000-ton chiller, 2,000-ton hotel with 500-ton machines. And you can see here from A to Z in different cities, the 100% load point. So let's look at Chicago. Happened 36% of the time with different condenser water than full load. The 75% load point happened 64% of the time, and the 50% load point never happened in a multiple chiller plant. Let's look at let's look at a 600-ton office with two 300-ton machines, and we see that an awful lot of times also, where in Chicago, and we analyzed all different cities throughout the world, we had Chicago 23%, 100%, 75% is 64.7, and the 50% load point happens 11.5, but the 25% load point never happens. Okay, so again, when we talk about the 23 XRV, it has a very big impact on lead. IPLV has a significant, it has a, basically you have to analyze IPLV. Oops, let me just go back to original slide. We have not only the fact, if you want to look at IPLV, we actually have the best IPLV, but I think you need to look at SPLV. We have a fantastic track record with this machine. We have multiple machines that are installed with customers that love the machine. So if you need to have a end user and discuss it with them, you just let me know. You could reach me and my email address. I think you have it via the webinar. You can email me or Ryan Hoger, depends on whose email you have. But you can contact me anytime. I'd be happy to give individual presentations if anybody wants them for their office. But really, this machine is an absolute, it's one of a kind. I can't say enough about it. What we're going to do the next month is we're going to take this machine and we're going to show how going from parallel to series counterflow, we can improve the efficiency on this particular machine. Even though it's fantastic efficiencies at full load, in parallel, we could put it in series and improve the efficiency 10 to 15%. Okay, that would be greater than 50% greater than the ASHRAE minimums in some cases. So it's a huge opportunity. Again, thank you for joining me. If you have any questions, please let me know. I will wait for questions. I think that's it. I'm going to sign off now. If anybody has any particular questions, I'm going to stop. You can get back to me. Thank you very much.